Hello and welcome to video number 12 in this series. And in this video I'll talk about how we obtain a rational expression when we divide one polynomial by another and how we can sometimes simplify the resulting rational expression. So in video number 10 in this series we talked about multiplying polynomials to get another polynomial. So as an example, if we take 2x squared plus 3 and multiply it by x minus 4, so I'm multiplying two polynomials together, I obtain 2x cubed minus 8x squared plus 3x minus 12, and that's another polynomial. But if instead of multiplying these two polynomials together, we divide them, so 2x squared plus 3 divided by x minus 4, then we're no longer in the family of polynomials because this is not a polynomial. And the name of this type of expression is, it's called a rational expression, one polynomial divided by another. In this case, we can't simplify this, so that's it. And another thing to note about rational expressions is that we can't have the denominator equal to 0 because then the expression is not defined. So we always have to, anytime we're dealing with a rational expression, is make sure that there's a note somewhere to say that this is only defined for all x. So this upside down A is a symbol that stands for all. So for all x not equal to 4, because if x was equal to 4, this would not be defined. So let's go through a few more examples of rational expressions, but we'll work with rational expressions where we can actually do a little bit of simplification using ideas about factoring that we explored in the last video. So here's another example of a rational expression, 2x cubed and 6x squared over 2x squared. And what we want to try and do is try and simplify this by pulling out any common factors. So let's factor the polynomial that's in the numerator, and then maybe there'll be some cancelling that we can do. So a common factor for the polynomial in the numerator here would be 2x squared. And then I would need to multiply by x to get the first term and by 3 to get the second term. And we can see now that we've got 2x squared in the numerator and 2x squared in the denominator, so we can cancel those. And we'll end up with just x plus 3. So in this case, we actually did end up with a polynomial. But actually we didn't, because we have to remember this notion of it's not defined when the denominator is 0. So this, we have to put a qualification that it's only defined for all x not equal to, the only value of x that makes this 0 would be 0 itself. So this resulted in x plus 3 for any value of x except for x equals 0. So that actually makes this not a polynomial, because polynomials don't have those restrictions. Let's do another example. Let's do x squared minus 4 and x squared plus 3x minus 10. So what I'm going to do is I'm going to see if I can factor the numerator and the denominator and see if we can get any cancelling going on. We should recognize this as perfect square minus another perfect square, so we can factor this using the idea of conjugates. So x minus 2, x plus 2. And then the denominator, if we can find two numbers that multiply to give me minus 10 and add to give me plus 3, I can factor this, and x, let's see, plus 5, x minus 2 works. And then I can see I've got a common factor in the numerator and the denominator, so I can cancel those. I end up with x plus 2 over x plus 5, but this is only valid for x's where the denominator is not equal to 0. So I'm not going to be able to use x equal minus 5 or x equal plus 2. Let's do another example. Let's do x squared plus x minus 12 and x minus 3 all squared. See if I can factor the numerator here. Two numbers that multiply to give me minus 12 and add to give me plus 1. So plus 4 and minus 3 would work. Plus 4 minus 3. And then we got x minus 3 squared in the denominator. So the x minus 3 in the numerator will cancel with one of those. X minus 3 is in the denominator. And we end up with x plus 4 over x minus 3. And again, I just got to put my domain restriction here. As long as x not equal to 3. Let's do a slightly more complicated example. Let's do x squared plus 4x plus 4 times 2x plus 2 divided by x squared minus 1 x plus 2. Okay, so see if I can factor that quadratic, x squared plus 4x plus 4. I need two numbers that multiply to give me 4 and add to give me 4. So, well, that's easy. So x plus 2 times x plus 2, so x plus 2 squared. There's a common factor here for the 2x plus 2, a common factor of 2. And then in the denominator, x squared minus 1, this is a difference of perfect squares, so I can factor that using conjugates. And then let's see if I can do any cancelling. One of the x plus 2's here could cancel with this one in the denominator. And the x plus 1 here could cancel with the one in the denominator. So I've ended up with 2 x plus 2 over x minus 1. Again, just put my domain restriction. As long as x is not equal to 1 or minus 1 or minus 2. So x not equal to, and I'll just put those in increasing order, minus 2, minus 1, and plus 1. So thinking about the ways that we've done this, pause the video at this point and see if you can work through the next two problems by yourself, and then restart the video and see if you get the same answers. So what we're trying to do is take a rational expression and simplify it by using factoring. So the first one, let's do 3x cubed plus 3x squared minus 18x, and we'll divide that by 6x squared minus 12x. And then the second one, let's make it a little more challenging. 2x minus 6, 3x squared plus 2x, and then 3x plus 2, and x squared minus 9. And so work through these two examples, simplify using the ideas of factoring, and also make a note of any values of x for which the rational function is not defined. So let's see how you did. This first one, so let's see if we can factor the numerator. So I can pull out a 3x. We'll have x squared plus x minus 6. And then let's factor the denominator too. I can pull out 6x. So I'll need an x and then a minus 2. And see if I can factor that quadratic up there, x squared plus x minus 6. I need two numbers that multiply to give me minus 6 and add to give me plus 1. So let's see, plus 3 minus 2 would work there. So I'll have 3x, x plus 3, and x minus 2. And then I've got 6x, x minus 2. And then let's see if I can do some cancelling. So the x and the x would cancel, the x minus 2 and the x minus 2 would cancel, and we got a 3 in the numerator and a 6 in the denominator. So I could cancel that, and it will leave me with 2 in the denominator. So my final answer is x plus 3 over 2, and just need to make sure that I'm noting down any values of x for which this rational expression is not defined. So it's not going to be defined when x is either 0 or 2. So for all x not equal to 0 or 2. And then the second one, let's see, I can pull out a common factor of 2 for that first term, and then a common factor of, let's see, x is all I can pull out of that second term. 3x plus 2. And then in the denominator, I got 3x plus 2. Then this is a difference of squares, so I can factor that using conjugates, x minus 3 and x plus 3. Let's see if I can do some cancelling now. I got x minus 3 in the numerator and the denominator. I got 3x plus 2 in the numerator and the denominator. So I end up with 2x in the numerator, x plus 3 in the denominator, and this is valid for all x not equal to, so if x was equal to minus 2/3, this first term, this first factor in the denominator would be 0, so that's not allowed. Or if x was plus 3 or minus 3. then we would end up with 0 in the denominator, and the rational function would not be defined. So x cannot equal minus 3 and minus 2/3 and plus 3. Any other value of x is fine. So that's it for this video, and in the next video we'll stay with rational expressions and we'll look at what happens when we multiply and divide rational expressions.